Question 1 then is a halogen displacement question. So we have chlorine and we have bromide ions, and you just have to remember that what always happens is that the element higher in the group attracts electrons more strongly, and so will always end up as a negative ion. So there is going to be a reaction because chlorine's higher in the group than bromine, so it's going to end up as the negative ion, and therefore the bromide ions will be oxidized. So first it just wants an ionic equation. For that, make sure you read the question. If you write the full equation with calcium bromide in there, you're not going to get the marks because the calcium ions are not involved. So what we have is the chlorine, which is aqueous, and we're adding that to bromide ions. So we have 2Br minus, and that will turn into 2Cl minus as the chlorine is reduced, and Br2 as the bromine is as the bromide is oxidized. So the observation is going to be that the solution will turn orange because the bromine is an orange colour. So now we have to do the calculation, and the first job is that we're given the concentration of the chlorine in grams per dm cubed, and you know that you're always going to need to turn that into moles per dm cubed. Chemistry calculations always revolve around moles, so as soon as you see grams you think, right, that needs to turn into moles. And it's simply a matter of saying that 7.00 grams per dm cubed is 7.00 over mR moles per dm cubed. Okay, because the per dm cubed bit is not changing. All you're doing is changing grams into moles, and you know how to do that. Mass equals moles divided by mR. So that's equal to 7.00 over 71.0 for Cl2, which comes to 0.9859. Sorry, 0.09859 moles per dm cubed. So that's the first step. So then it tells us that the bromide is in excess, so what we need to do is to work out how many moles of this we've got. So we just get moles is concentration times volume in dm cubed, and we've got the concentration because we've just worked it out, so it's 0.09859, and the volume of chlorine solution that we're adding is 50 cm cubed, so that's 0.0500 dm cubed, and that works out to be 0.004930 moles of Cl2. So now we get to the main issue, which is that we're supposed to be working out delta H for this reaction, and the key to that is always this relationship, Q is equal to mc delta T. So you need to memorize that and remember what the terms mean. So M is the total mass of the stuff that's being heated or cooled. In this case heated because the temperature rises, but it could be cooled if it was an endothermic reaction. C is the specific heat capacity, and in chemistry A level that's almost certainly going to be of water, and we assume that applies to aqueous solutions such as we have in this experiment as well. And delta T is obviously the temperature change. So you need to remember what those terms mean, not just memorize the equation. Especially M is the one people are likely to get wrong. It's not the mass of what's reacting, it's the mass of what's being heated up, which is in this case the mass of the solution. So we've got to think where we get those numbers from. Now M comes from the fact that we have a total volume of 50 plus 50 is 100 cm cubed. So we have 100 cm cubed total volume, and that's what the heat is being spread out through, and we assume that we have a density of 1 gram per cm cubed for aqueous solutions. You always make that assumption, that if they don't tell you the mass of the solution, you work it out from the volume by assuming the density is 1 gram per cm cubed, which means that the volume in cm cubed is equal to the mass in grams. Okay, so that's the key. So because we know we have 100 cm cubed altogether, m will be 100 grams. C is the specific heat capacity of water, which comes from your data sheet and is 4.18 joules per Kelvin per gram. And delta T is the temperature rise, which we're told is 1.1 degrees C. So we multiply those numbers together and we get 459.8 joules. Okay, you know it's going to be joules rather than kilojoules at this point because the number that you're feeding in, the specific heat capacity, is where the joules come in, and that's joules rather than kilojoules. So if you can't quite remember that the units tell you a lot. Okay, so 459.8 joules, and we're going to need to turn that into kilojoules for the purposes of a chemistry calculation. So we divide by 1,000 and get 0.4598 kilojoules. Now what we need is kilojoules per mole. We want the enthalpy change. And the relationship that we need is that delta H is minus Q divided by the number of moles reacting. And the minus is only there because we know this is an exothermic reaction. If it was endothermic, it would be plus Q over moles. So always remind yourself that that sign depends on whether it's exothermic or endothermic. But for an exothermic reaction, we know it's going to be negative. So it's minus Q over moles, which is minus 0.4598, divided by the number of moles that we worked out earlier, which was 0.004930. And that works out as minus 93 kilojoules per mole. And I've limited that to two significant figures because the temperature rise was only two figures. So although we knew these numbers more accurately, these were known to three figures, the temperature rise was only two, and therefore we need to limit the answer to two significant figures. And so that's the answer. Part C wants to know what difference it would have made if these bromide ions came from magnesium bromide instead of calcium bromide. So this is a way of testing whether you've really understood that once you dissolve an ionic compound in solution, the ions are completely separate. And that's why when we write the ionic equation like this, the magnesium ions or calcium ions are not there, because they are spectator ions. In the original experiment we had calcium ions floating around at the beginning, and they were still there at the end. They didn't change in any way. So they weren't involved in the reaction, they don't affect the delta H therefore. And if we replace them by magnesium ions, again, they're just not going to be involved in the reaction, so again it won't make any difference, and so the answer is that delta H is the same. So it's just a way of testing that you've really understood that point, that when you dissolve an ionic substance, the ions become separate and they react separately, and typically you get the so-called spectator ions, which are just not involved in the reaction. And then we have to explain why calcium bromide solution does react with chlorine but does not react with iodine. So this is the question you have to expect when you get these halogen displacement experiments. So what it comes down to is the fact that chlorine has fewer shells of electrons than iodine. And that means that outer shell electrons are more strongly attracted to chlorine's nucleus than to iodine's. Okay, this is the classic trend down the group thing, which you learn when you're learning ionization energies, but it applies in other contexts too. It applies when you're thinking about electronegativity, and it applies here when you're thinking about ability to gain an extra electron. So the outer shell electrons are more strongly attracted to the nucleus. Make sure it's clear that the attraction is to the nucleus of Cl than iodine. And you have to spell out why that is. Just saying fewer electron shells isn't really enough. So spell out that that's because they are closer to the nucleus and also less shielded. Okay, remember all the factors that you talk about for ionization energies, you talk about here too. So they're closer to the nucleus and less shielded in chlorine. And for completeness, you should also mention that this outweighs chlorine's lower nuclear charge, because that on its own would give you the opposite trend. So, but it's outweighed by these other things. So this outweighs the lower nuclear charge of chlorine. So that's fundamentally the reason that chlorine is better at attracting an electron into its outer shell than bromine is, but iodine is worse. And so we need to sort of say that explicitly, that chlorine attracts an extra electron better than, let's try that other way around. I want to say that bromine, attracts an extra electron better than iodine. So once you've got Br minus, iodine can't take that extra electron away from it, but less well than chlorine. So when chlorine comes along, it's able to grab the extra electron from Br minus. And that answers the question. So once you've revised ionization energies, it's all the same ideas, but you don't talk about ionization energy because we're not talking about losing electrons, we're talking about gaining them. And you don't talk about electronegativity, because electronegativity is about how strongly you attract shared electrons, but again, we're not sharing them, we're transferring them. So if you talk about either of those things explicitly, you're missing the point and you're not going to get the marks. But the ideas behind it all relate to attracting electrons in the outer shell. So it's all the same argument, but you just have to make sure they're focused on the relevant issue here, which is ability to attract an extra electron. Part E wants us to find the enthalpy change of solution of calcium bromide using these data. So the best way to do that is to set up a Born-Haber cycle. So remember, the overall change starts with the solid calcium bromide, so we can put that down as an enthalpy level. And as always with these things, make sure you put the state symbols in to make it clear what's going on. And what we're going to end up with are the separate ions in aqueous solution. So this is our final state. I have guessed here that delta H of solution, which is this overall change, I've guessed it's going to be exothermic. It might turn out to be endothermic, in which case this level should properly be up there, but it won't affect the calculation, so there's no problem about just setting up the cycle like that. So then we break it down into steps. And so you think, right, what do we have to do first to the solid? And the answer is, well, you have to break up those ionic bonds. If you do that, you separate out the ions, and if all the ions are completely separate, they're going to be gaseous. So the next step is that we're going to get gaseous Ca2+ and bromide ions, and that's going to be a strongly positive delta H because we're putting energy in to break up all those ionic bonds, and more specifically it's the opposite of the lattice enthalpy. Okay, because lattice enthalpy is when you make a mole of the compound from its gaseous ions, but here we're doing the reverse of that. We're taking the compound and breaking it up into its gaseous ions. So we just take the lattice enthalpy number and we change the sign because we're going in the opposite direction. So that will be plus 2170 going down there. And then we simply hydrate the ions. Remember, that's what these enthalpy changes of hydration are, is taking a mole of gaseous ions and transferring them into aqueous solution. So we're going to do that in 2 stages, doing first the calcium ions and then the bromide ions. So this intermediate level will have aqueous calcium 2 plus, but still gaseous bromide ions. And you can see that hydration of a mole of calcium ions is minus 1579. So we get that there. And we have to be careful with the bromide because there are 2 moles. So it's minus 348 for 1 mole, but we've got 2 moles, so it's minus 348 times 2, which is minus 696 kilojoules per mole for that step. And then we simply say, right, this is our what we want. This is our delta H that we're trying to calculate, and we're just going to follow that pathway. We're going to go up there, and down there, and down there. And so we get that delta H of solution is plus 2170 minus 1579 minus 696, which comes out as minus 105 kilojoules per mole. Okay, so solution cycles are actually much simpler than the formation cycles just because there are fewer steps involved. And you can see the logic is very simple. You just break up the existing lattice and then form the new hydration interactions with the water, and that's all that's involved. So for part F, we have to bring together these 2 enthalpy changes that we've now calculated. So in part B, we calculated the enthalpy change when aqueous calcium bromide reacted with chlorine. I've written it now as a full equation rather than an ionic equation, but remember it's the same thing. It's just that the calcium ions weren't actually involved in the reaction, but that's the correct full equation. And then from part E, we've got a different change, which is what does it take to go from solid calcium bromide to aqueous calcium bromide. So you can see that if we want to start with calcium bromide solid and add it to chlorine, we have to do these 2 steps successively. We have to get that into solution, and then we have to do the reaction. And so you can sort of see what the answer is going to be really just by thinking that through. But formally, the neatest way to show that is to draw a Hess's law cycle and say, right, our starting point is that we've got solid calcium bromide plus aqueous chlorine. Okay, and we're wanting to turn that into aqueous calcium chloride plus bromine. Okay, so that's the one that we want to find, delta H. And we just break it down into 2 steps and say, right, first we turn that into aqueous calcium bromide plus chlorine, and then we do the reaction. The aqueous calcium bromide then reacts with the chlorine to give you your product. Okay, so we're just simply doing the normal Hess's law thing and saying, right, that is the pathway that leads to the overall change we're looking for, adding solid calcium bromide to aqueous chlorine. The first step is just the dissolving of a mole of calcium bromide, so that's this one, is minus 105. The second step is the reaction of aqueous calcium bromide to form aqueous calcium chloride, so that's this one, is minus 93. And you can see that the 2 legs of our journey both go the same way as the arrows we've put on there. So delta H, the one that we want, is simply minus 105 minus 93 is minus 198 kilojoules per mole.